Next is this phenomenon that when you have a wave packet and it moves, it can change shape and get distorted. And that is a very nice phenomenon that takes place in general and causes technological complications, and it's conceptually interesting. So let's discuss it. So it's still wave packets, but now we have to go back and add some time to it. So shape changes. So we had a psi of x and t is equal 1 over square root of 2 pi phi of k e to the I kx e to the minus I omega of k t. And what did we do with this to analyze how it propagates? We expanded omega of k as omega of k naught, which again, this quantity is centered and peaks around k naught, plus k minus k naught times the omega dk at k naught, plus 1/2 k minus k naught squared the second omega dk squared at k naught. And it might seem that this goes on forever. And what did we do before? We looked at this thing and we did the integral with this term and ignored the next. And with this term, we discovered that the profile moves with this velocity, the group velocity. Now we want to go back and at least get an idea of how this term could change the result. And it would change the result by deforming the shape of the packet. So it is of interest to know, for example, how long you have to wait before your packet gets totally deformed, or how do you evolve a packet. So we need to recall these derivatives. So the omega dk is the same as dE dP by multiplying by h bar. And this, you remember, was p over m. The EdP is p over m. And it's equal to h bar k over m. So the second omega dk squared, I must differentiate the first derivative with respect to k. So I differentiate the first derivative with respect to k, and now I get just h bar over m, which is quite nice. And the third derivative, the 3 omega dk cubed, is 0. And therefore, I didn't have to worry about these terms. The series terminates. The Taylor series terminates for this term. Yes?
The reason this happens is because we're still non-relativistic, right?
That's right. So what is it that we get? Well, this term is roughly then 1/2 k minus k naught squared times h bar over m. And we can go back to the integral that we're trying to do. We don't do it again, or not by any means, but just observe what's going on there. And we have an e to the minus I omega of kt that we did take into account, but the term that we're dropping now is a term that is minus I omega of k, well, whatever we have here, 1/2 k minus k naught squared h bar over m t. That's the phase that we ignored before. But now we'll just say that we expect, therefore, that the shape doesn't change as long as we can ignore this phase. And this phase would start changing shape of the object. So our statement is going to be that we have no shape. So let's imagine you started with a packet at some time t equals 0. And then you let time go by. Well, there's some numbers here and time is increasing. At some point, this phase is going to become unignorable, and it's going to start affecting everything. But we have no shape change, or no appreciable shape change, as long as this quantity is much less than 1. So as long as, say, k minus k naught squared h bar over m, absolute value of t, is much less than 1. No shape change. Now, it's convenient to write it in terms of things that are more familiar. So we should estimate this thing. Now, we're doing estimates in a very direct and rough way here. But look, your integrals are around k naught. And as you remember, they just extend a little bit because it has some width. So k minus k naught, as you do the integral over k, you're basically saying this thing is about the size of the uncertainty in k. So I'll put here delta k squared. Then you'll have h bar t over m much less than 1. Now, h bar times delta k is delta p. So this equation is also of the form delta p squared t over h bar m much less than 1. There's several forms of this equation that is kind of nice. So this is a particularly nice form. So if you know the uncertainty in momentum of your packet or wave packet, you know up to what time you can wait and there's no big deformation of this wave packet. Another thing you can do is involve the uncertainty in x, because, well, delta p, delta x is equal to h bar, so we can do that. And so with delta p times delta x equal to about h bar, you can write t less than h bar over m over delta p squared, which would be h squared delta x squared. I think I'm getting it right. Yep. So T much less than m over h bar delta x squared. That's another way you could write this inequality. There is one way to write the inequality that you can intuitively feel you understand what's happening. And take this form A from A, write it as delta P T over M less than H bar over delta P. And H bar over delta P is delta X. So here you go delta P over M T less than or equal, or much less, I'm sorry, much less than delta X. I think this is understandable. You see, why does the packet change shape? The reason it changes shape is because the group velocity is not the same for all the frequencies. The packet mostly moves with k naught, and we evaluated the group velocity in k naught. But if it would have a definite velocity, it would have a definite momentum. But that's not possible. These things have uncertainty in momentum, and they have uncertainty in k, that we use it to write it. So different parts of the wave can move with different velocities, different group velocities. The group velocity you evaluated at k naught, but some part of the packet is propagating with group velocities that are near k naught, but not exactly there. So you have a dispersion in the velocity, which is an uncertainty in the velocity or an uncertainty in the momentum. Think the momentum divided by mass is velocity. So here it is, an uncertainty in the velocity. And if you multiply the uncertainty in the velocity times this time that you can wait, then the change in shape is not much. If this product, which is the difference of how one part moves with respect to the other, difference of velocity of time, is still smaller than the sort of uncertainty that controls the shape of the packet. So the packet has a delta x. A delta x. And as long as this part, the left part of the packet and the top of the packet, the difference of velocities times the time, it just still, compared to delta x, is small, then the thing doesn't change much. So I think this is one neat way of seeing what an equation that you sometimes use in this form, sometimes use in this form. It's just things that you can use in different ways. So for example, I will not, well, I can do this, a little exercise. If you have delta x equals 10 to the minus 10 meters, that's atomic size for an electron. What is the, how long does it remain localized? So you have an electron and you produce a packet and you localize it to the size of an atom. how long can you wait before this electron is just all over the room? Well, when we say this t and we say this time, we're basically saying that it's roughly still there, maybe grew 20%, 30%, but what's the rough time that you can expect that it stays there? So in this case, we can use just this formula, and we say the time could be approximately m over h bar delta x squared. It's fun to see the numbers. You would calculate it with mc squared over h bar c times delta x over c, this squared. The answer is about 10 to the minus 16 seconds, not much. This is kind of a practical issue in accelerators as well, particle physics accelerators. They conserve bunches. A little bunch of protons in the LHC is a little cylinder in which the wave functions of the protons are all collimated, very thin, short, a couple of centimeters short. And after going around many times around the accelerator, they always have to be compressed and kept back, sent back to shape, because just of diffusion, these things just propagate. And so it's a rather important thing.